Hello, everybody. This is some examples on Jordan forms for the class Maths 2009 at University of New South Wales. This time we are doing the question 92. We have 2 by 2 matrix. We would like to show first A is not diagonalizable, and we will explain why generalized eigenspace of A is C2. We will find a basis consists of a chain of generalized eigenvectors of A. And we will write A as a multiplications of P, J, P inverse. J will be the Jordan form, and P is an invertible matrix. So these are the things that we are going to do in this example. For to show that non-diagonalizable, we need to calculate eigenvalues and eigenvectors. So for eigenvalue, first we would like to calculate the characteristic polynomial of the matrix. So that's the matrix. That's A minus lambda I. So we are taking minus lambda on the diagonal and calculating the determinant, this times this minus this times this. That's the polynomial of degree 2. And that's 49. That's 7 times 7 is 49. So this one can be written as linear factor lambda minus 7 squared. It means that lambda is equal to 7 is an eigenvalue with algebraic multiplicity 2. Algebraic multiplicity, as definition, just reminding ourselves, that is the order or is the degree of the root of that eigenvalue. So the root is minus 7, and minus 7 has degree 2 in this polynomial. Then the eigenvalue the algebraic multiplicity of the eigenvalue 7 is 2. Then next step is to calculate the eigenspace E7, and that is the kernel of A minus lambda I. That is kernel. Now we will put the 7 instead of the lambda in here. So 10 minus 7 is 3. 4 minus 7 is minus 3. So we need to calculate the register of echelon form this matrix because we would like to find out the basis of the kernel space. So this is just 3 times this. And if you multiply this row by 3 and add this row, we get 0, 0. The solution space of the kernel space, or the solution of this matrix times xy is equal to 0 vector, is that y is free, a variable, and 3x minus y is equal 3x plus y is equal to 0, which means that 3x is equal to minus y. Then if you put x is equal to 1, then y will be minus 3. So we can choose this one as a simple representation of basis of this space. So this span space is the all multiple, means that we are taking all multiples of this vector. So this is the basis of the eigenspace, 7 eigenspace. But the dimension of this space is 1. That is the geometric multiplicity. That's by definition. Geometric multiplicity is the dimension of the eigenspace of the corresponding eigenvalue. The eigenvalue is 7. Geometric multiplicity of 7 is 1 dimension. Here we have algebraic multiplicity is 2, but the geometric multiplicity is 1. So they are different. If this is the case, then we say cannot be diagonalizable. If we have 2 vectors here, if the dimension is 2, if algebraic multiplicity is equal to geometric multiplicity, which means that geometric multiplicity is 2, then we will have 2 vectors, 2 basis vectors, 2 linearly independent vectors here. Since you have 2 by 2 matrices, these 2 vectors would span the whole space, because the vectors that you're obtaining in that way are linearly independent. And then you're thinking the spanning of those 2 vectors, it means that it will give you the whole space. Okay, then with this situation, since we have algebraic multiplicity 7 and geometric multiplicity is 1, it means that we have Jordan block 1. That is, you have 7, 7 on the diagonal, and you have 1 here. This is the place that says that you cannot be separable. Think about the situation. If you had two vectors, if you obtain two vectors here, then the Jordan form that you're going to obtain will be J17 and J17. That would be just 7007, which is like the block. So this is one block, and then you will have, you will have this block, right? You have one block of this, one block of that. Right? So you have one block of this, one block of, if you had two ion vectors, if you found two ion vectors here, this would be the case. And in that case, the situation will be A will be diagonalizable. But here we found one ion vector, geometric multiplicity is 1, whereas algebraic multiplicity is 2. We haven't found enough vector to give us a basis for the whole space. Then A cannot be diagonalizable. We cannot do this. We have to think about this situation. Okay, this is the Jordan form. This is the Jordan form corresponding to ion value 7. Okay, what is I would like to explain a little bit of the general theory here that we are going to use. If you have a matrix A, this is just a definition of the generalized ion space, because the next step that you would like to do is calculate the generalized ion space of the lambda. So the lambda is the ion value, and generalized ion space denoted with this notation of the matrix A. This is by definition, this notation means by definition, is equal to the sum of the all kernel spaces A minus lambda I to the K. So A minus lambda I to the K, you're thinking the powers of these matrices, and then you're looking at one by one is the kernel. For shortcut, sometimes we write those vector spaces as VK lambda. This is a shortcut for this vector space. This is just a notation from here to here, just a change of a notation. And dimensions of the spaces, or dimension of this one or dimension of this one, is dk. And you can, if you want to specify the ion value, you can use the lambda here for the ion value. But we usually use dk for our cases. So this one is called the nullity of the vector space vk lambda, or nullity of this space. K, this K represents the power of A minus lambda I. The theory tells us something very important. Theory says that this sum is finite. In certain period, certain power later, everything turns out to be exactly the same. And theory says that these dimensions is really from smaller than higher. Right. That exists a sequence of the increasing sequence here. And also theory says that the key thing here, why it is working, this is what I want to say here. The key idea, this is a key idea here. This is the key idea here. For any matrix, the kernel of M is inside the kernel of M square, kernel of M cube, and so on. Everything is one to another, it's included. So it is the same story here. So this one is included, kernel A minus I is included in kernel A minus I square, and so on. So when all these powers is like a sequence in each other. It's inside of each other, or you can think of as a circle of the. You can think of as like this one and this one and this one. So it is like a circle to circle to circle to circle. Right? That's so that's the key idea. This is why it works. This ends in some stage, and they are all one to inside. Everything works with that idea. And this means that there's finite. It means that there exists an integer, and it lists integer, and all the others are exactly the same space afterwards. For example, if it finishes in the power 3, all of power 4 is equivalent to this space, power 5 is equivalent to this space, and so on. And also there's a nice nice properties about this the space dimensions. And we are going to use those ones to calculate the certain things later on. So these equations, the dimensions of this spaces are really important. So decays are really important. And one of the things that the decay satisfies, decays are always increasing. So it increases, and there is no pause in them. If one of them stops growing, it means that it is the end of it. There needs to be end of it. And there are certain properties of these dimensions. And there's no pause, it grows. If it stops, then same for a while and grows again. This kind of situation does not happen. The no pause means is this does not happen. So this is a general knowledge, general information that I would like to give about the generalized eigenspaces, because the next things that we would like to practice is just to find the general eigenspace for A. And for us, we have only one eigen value for this small example. So this is just a notation, is the first power of the kernel A minus I. This is what we calculated. We just found one vector, that dimension 1. So we found D1 is 1. If we calculate the second power, just multiplying this matrix by itself, we found 3. 0, 0, 0, 0. This means that this is everything, right? Because every vector satisfies this condition, what I'm trying to say here. So for any vector v, so a minus 7i square v is equal to 0. This implies this is always the case because this one is 0. The matrix itself is 0. So this matrix times any vector will be 0. So you will obtain as kernel of a minus 7i squared will be the whole space. Now here, since we are, when you're looking at the generalized eigenspaces, we think about our matrices over the complex numbers, because complex numbers are algebraically closed, which means that every polynomial has roots in complex numbers. That this is not the case for the real numbers or rational numbers. It is the key idea is that the complex numbers are algebraically closed. Every polynomial are solvable. All the roots of a polynomials are inside the complex numbers. So this is why we are thinking the matrix over the scene complex numbers. So there are vector spaces, complex vector spaces. So this one needs to be the whole space. So the generalized eigenspace of 7 will be the first power, the kernel of the first power, kernel of the second power, kernel of the third power. But after third power, everything really is itself, right? This one is equal to that one, this one is equal to that one, and this one is inside that one, and this one is equal to that one. So if you see the picture here, it's all C2. So all C2, adding C2s and C2s and C2s infinitely times, you have C2. So this is the two-dimensional complex space. So this is our generalized eigenspace for 7. So just C2. And this usually has diagram. Sometimes we denote it with the blocks like that. We will going to use these blocks later on. We will talk about these blocks later on. That represents the two-dimensional space. Okay, now the next step we found, this was the question, right? We found the generalized eigenspace. Yeah, that was the question. We found this part. We found this part. We found this part. Now we want a basis corresponding the chain, consisting of a chain of the generalized eigenvectors that will allow us to construct the P matrix and J matrix, right? We construct the J matrix because we found the J matrix. But in order to be able to construct the P matrix, we need to look at the chain of the generalized eigenvectors. Just waiting for the computer to read. Okay. For this one, what we know, so this is, any vector is in this vector space means that satisfies this equation. The vector in this kernel means that A minus 7 times B is equal to 0. That is, that vector is an eigenvector of 7. That's what it is. Right? This is by definition of the eigenspace. This is an eigenvalue. This is an eigenvector. This is just by definition. I'm not repeating anything else. But this is the one, and this is the one equation that I'm going to use to construct the matrix, invertible matrix P in the equation that we have. Now we are going to choose a V2 such that V2 is linearly independent with V1. And V2 is inside the square, which is the C in C2, but not in V1, right? Because we want linearly independent with the eigenvector V1. We want to put a chain now. So anything different from V1, I just would like to find out the vector that show you. That is the vector. Here. The vector is 1 minus 3. So any multiple of this vector is inside here. So we want different vectors, any multiples of this vector. So if you look at this vector here, now if we choose, for example, 1, 0, usually try to think about the first choices as standard vectors, simple vectors. Try to choose the simple vectors, which is not in V17, which is not in the first order of this one. 1, 0 does, right? 1, 0 is different from the 1, 3. Then apply the A minus 7I to V2. This is this matrix times 1, 0. This times this is 3. This times this is minus 9. This is 3 times 1 over minus 3. So this is inside the V1, 7, level 1 generalized eigenvector. This is equal to really kernel A minus 7I. This is the first order. There's the first one. The key idea here is that to obtain this equation, this is what we want, this equation. So this equation means that I think I want to Okay, that's, I should have said this equation in somewhere here rather than there, because it is confusion later on. So this equation should be here. Right, because this V1 is inside the kernel of A minus 7i, and it satisfies this equation. So this equation gives me this one because A V2 and 7V2, take it to the right-hand side. Right-hand side, we already have V1. That will be 7V2. We know that this kernel space means this is an ion vector of 7 in the level 1. So this equation satisfies. Why I want this two equation? So these two equations is this one and this one. So V1, V2. So I'm thinking like a block multiplications of the matrices. So this is the matrix A, and this is the matrix V1, V2, and then V1, V2. If you multiply AV1 is equal to 7V1. So this times something will give me 7. So 7107, which is our Jordan form. This is just a figuring out. So from this equation gives me this matrix equation. That's what I'm trying to say here. This equation gives me this matrix equation, right? This times this AV1 is equal to 7V1, which is this row with this column, 7V1 plus 0V2, right? This one is satisfied. So this equation, AV2, it's AV2 on the left-hand side. On the right-hand side, this vector with this column, V1 plus 7V2, which is this equation on the right-hand side. So this equation is exactly this matrix equation. And then this matrix is called P, and this matrix are J matrix, Jordan form that we calculated previously in the question. Okay, so if you multiply P inverse with this from here, from the right-hand side, you will have a P inverse here. But since you have a P here, P times P inverse will give you identity on the left-hand side here. You will left only A, which is A. So A is equal to PJP inverse. The P matrix here, as we've done, this is 3 minus 9. This is the V1, and this is V2, right? This is V2, this is V1. This is a P matrix. And since it's a 2 by 2 matrix, it is easy to calculate the inverse. This is a formula. This is the green part here gives you the formula for the inverse, P inverse. This times this minus this times this is just 1 over 9. So AD minus BC is 9, which is basically the determinant, as you realized. And this will be, you swap the diagonal entries. So 3, 0 will be 0, 3. And then you put the minuses on the opposite diagonals. This is minus 1, and minus 9 will be 9. So this P inverse. You can check this matrix by just multiplying these matrices, and you should obtain A. You can do that. Or you can do as a checking thing, you can AP is PJ. So if you multiply A, this is P, A times B will be giving you this kind, and P times J will give us this time, and both of them correct. So this is a checking thing for you. So you don't need to do this part, but that is the case. So what we've done, we took a V2 in the pool space, and then we construct a chain from V2 to the V1. It's a one-level chain, and that corresponds to the Jordan form J27. I think this explanation is helpful for you. Thank you very much. And I will continue sending more videos on the Jordan forms, just reminding you. we have more things to say on Jordan forms. Thank you.